One important job of a hydrologist is to predict the response of a stream to some kind of precipitation event. So imagine there's some kind of precipitation event within a watershed, and the stream is going to respond with an event hydrograph. This is a typical event hydrograph I've shown here, right, where you see the discharge suddenly increase and then actually decrease again as the precipitation event after the precipitation event ended. And you can imagine why knowing what the shape of this hydrograph looks like would be really important for some people. It would be important, for example, for people living downstream who might be worried about flooding. It could be important to farmers who are using this water for irrigation and they want to know how much water does the stream carry. It could be important for engineers who are trying to design bridges who have to be able to withstand a certain discharge or stage. So again, knowing what the shape of this discharge looks like is really important, and we'd like to be able to predict what it is based on rainfall events which are causing the event hydrograph, this surge to occur in the first place. So, although there are a lot of methods that actually do this, they all boil down to the same basic idea. You have some kind of triggering precipitation event over the watershed. I'm just going to call that P. That's the precipitation that's falling. Usually it's thought to occur all over the watershed, and that's the water that's going to enter the stream and cause the stream to rise and the discharge of the stream to rise. But in fact, not all of that precipitation is going to make it quickly to the stream, right? Because some of that precipitation is going to be lost to evapotranspiration, or some of it's going to infiltrate the ground. And so what we're really interested in, what we're going to call the effective precipitation, or P star. And that represents that portion of precipitation that makes it quickly into the stream, either by processes of overland flow, or maybe it's subsurface storm flow, or maybe it's saturation overland flow. By whatever process, this water is getting quickly to the stream, and it's going to cause the stream to respond. The stream responds by its hydrograph, right? So the stream, this is the thing we want to know, right? This is the hydrograph of the stream in response to that input of waters. But in fact, that's not all the water that the stream is carrying, right? Because in most cases, the stream is also carrying base flow, which would have been there anyway, even in the absence of a precipitation event. So the actual stream discharge is in fact greater than that Q star, the rise, that additional water added to the stream due to effective precipitation. And the actual output hydrograph, the actual hydrograph of the stream, the discharge of the stream here, is actually something that we measure, right? This is what we actually measure. We're measuring the output discharge of the stream, and what we want to know, what we want to be able to predict, is we want to be able to predict, if I give it this, if I give it some precipitation over the watershed, what will be the output hydrograph of the stream. This is the whole idea behind this kind of stream analysis. Now, in doing that, there are going to be two parts we have to pay a little attention to. There's this part here where we partition the total precipitation into effective precipitation and losses. And then there's the part here, which we've actually already done, which is where we partition the stream flow into the storm flow and base flow. Let me quickly review what we've done, because we already did that during the last class. So here we have a typical event hydrograph, right? This is discharge measured versus time. This time period is maybe a couple days, maybe as long as a week. So we have an initial base flow recession portion of the curve, and then all of a sudden water starts entering the stream, discharge rises to a peak, and then it returns, it starts to descend again, it decreases again, eventually reaching that continuous base flow level that occurs even in the absence of precipitation events. And remember that the area underneath this curve represents volume, and what we want to do is separate out the volume due to the precipitation event and the volume due to base flow. And there are several different methods of doing that. In the absence of the really theoretical ones and the really computational ones, most people take a sort of empirical, simple approach to doing this. And let me quickly review some of the more popular ones. So probably the simplest thing you could do was just find the point where you start seeing storm flow occurring. That is where you start seeing the discharge increase, and you draw a straight line across the hydrograph like this. And then you assume that's supposed to be straight. You assume everything underneath that is base flow, and everything above that between the hydrograph curve and that blue line represents a volume of water added by event flow. So essentially what you're assuming is that base flow is remaining constant through the duration of the storm event. Now, sometimes you can actually see a little kink on the downward limb of the hydrograph. Let's assume that there's a kink right here. There really isn't, but what if we could see one right here? And we would therefore, we would sometimes interpret that to mean that this is the end of the storm flow event, storm flow additions, and that after this kink, at times after that kink, we're resuming the normal base flow only flow of the stream. And so identifying that kink would allow us to then separate out the hydrograph into base flow and storm flow simply like this, where now this represents the storm flow and everything beneath that represents the base flow. Then there are methods that take advantage of the theory that says that the base flow portion of the hydrograph should be an exponential decay curve. So one thing we could do, for example, is to extrapolate the pre-storm base flow curve, that's just using sort of an exponential decay curve down like this. And this then is our prediction of what the base flow would have looked like during the stream event. We then typically find the intersection of that recession curve and the peak, and then we'll draw another line from here to the end of the storm flow event, which is either recognized either as a kink, or in the absence of a kink, there are expressions that actually calculate the time it would take typically for the storm flow to be exhausted, and where we return back to the base flow portion of the falling limb of the hydrograph. And so this would now represent our storm flow, and everything underneath it would represent base flow. We can also back extrapolate the recession curve at the far end of the hydrograph, right? So if this represents the hydrograph, just base flow, we can back extrapolate that. And if we see that the base flow recession curve goes like this, we can then say, oh, this must then represent the time when we return to just base flow, and everything to the left here would represent some contribution of storm flow. And then there's a whole bunch of things. We could either join this directly like this, or we could actually extrapolate forward like this on the pre-storm recession curve and do this. There's a bunch of different things we could do, all with the goal of getting somewhat of an accurate estimate of the amount of storm flow versus base flow. And once again, the reason we do all this is because this amount of the storm flow, the area under the curve, remember this represents a volume of water. This represents the water added to the stream from the precipitation event, the storm flow. And we're going to equate that. Remember, if we think about it, this has to exactly equal the effective precipitation. We're just taking that water from the watershed, and it's going into the stream, and it's causing this amount of stream flow. And this is precisely then the relationship we're looking to somehow be able to make the prediction then between this, not only the volume is pretty straightforward, right? The total volume of effective precipitation is equal to the volume of Q star, but we also want to know something about the shape of this portion of the hydrograph, and that's what I'm going to be talking about next.